Good morning, everyone. So my name is Jeremy Warren. I am the project coordinator of Tempest, and I am also the chair of the EU Ingenious Cluster, which which regroups the 5 projects funded underneath the same call. And we'll talk about that a little bit later. But the Tempest project was designed to create essentially a new box of tools for batteries to promote safe by design, recyclable and high performance and lightweight batteries. Our goal was to move beyond, I guess, the standard design of batteries and look at how we can reduce weight, make them safer, and really do everything we can to increase performance and also sustainability. And so, as you'll see today, as I said, we're trying to bring together a nice unified toolkit that can be adapted to all sorts of future generations of batteries. And so our objectives, first of all, was to bring new cell technology. So in Tempest, we focused both on Generation 3 lithium-ion cells, but we also include semi-solid state batteries as well. So we're trying to address both of them. And then we also look at new architectures and designs. So we are moving from module-based towards cell-to-pack designs for increased packing density. And we're also moving towards composite housings instead of metal housings for vastly reduced weight. There are numerous technologies for thermal management, both in preheating the cells, for example, if it's at freezing outside, so that you can get them up to their optimal operating temperature, but also to improve the evacuation of heat during if they get too hot. And then finally, there are several approaches that are implemented to increase the safety, both in terms of resistance to abrasion and impact, resistance to external fire sources, and integrated systems for structural health monitoring. In addition, we also look at how to improve the circularity of these systems. And this is not just from an optimized disassembly approach. This is also a methods that we use to very cleanly recycle the black mass at end of life to recover both the metals as cleanly as possible without going through pyrometallurgy or hydrometallurgy, I should point out, and also methods to treat the graphite and reuse it in other approaches. And then finally, there are also, we look at models for the optimization of batteries and work towards sustainable value chains. So overall, we can just summarize the main technological impacts in 4 points. We want to increase the recyclability by 70%. We want to improve the costs of manufacturing by 30%, increase the battery performance by 15%, and reduce the weight by 15%. And on this latter point, we have actually gone way beyond that particular KPI. Now, the environmental benefits are varied. I should point out that within the context of this call, integration of the battery packs into specific demonstrators and the actual integration was not covered under this call. And so the 3 demonstrators that we develop in this call were actually designed to be representative demonstrators. So they aren't for vehicle X or Y or Z. They are different sizes that are representative of different types of applications. But nevertheless, we can look at the potential environmental benefits based upon what we know from the literature and also from what has come out of the sustainability assessments that have been performed within the project. So we want to look at reducing the greenhouse and aerosol production by up to 62%, reduce the energy loss and increasing the range by up to 52%, dramatically reduce the amount of carbon dioxide emitted, reduce the energy loss, and reduce the overall energy load, especially for stationary storage, by implementing new and improved systems for stationary storage. And so if we look at the overall technologies, which I described earlier, so we're looking at cell-to-pack architectures in terms of the overall design. And we look at next generation, both generation 3 and generation 4 cells. And these are generation 4A, I should point out, because they're semi-solid state. And then from safety, this is one of the places where we are really pushing the envelope because of the fact that we are using composite housings and their mechanical behavior is quite different from what is the state-of-the-art, i.e. metal housings. We also wanted to integrate in, it was a good opportunity to integrate in structural health monitoring. So you'll see as we move through this that that there has been technologies developed by by KTU in structural health monitoring that will allow a car that is equipped with these types of systems to detect basically fissures that form from impacts and essentially warn a driver that you have a problem with the housing, go seek assistance as soon as possible before a thermal runaway situation can occur. And as I said, also there are flame retardant systems and also coatings for auto extinguishing within the interior of the housings, and thermal management systems and impact resistance. And then in sustainability, we have done a lot towards effective disassembly through the use of desponding on command adhesives, and advanced and novel approaches, hydrogen-based recycling methods, to really look at new ways of recovering and reusing the materials. Okay, so the project basically focuses on 5 specific aspects. So first of all, in the demonstrators, we basically in the breakdown of the work that we accomplished, our first goal was just to design the specifications and the circularity models. And then we started looking at how do you optimize the architecture across the 3 demonstrators, which you will see later on. How do you look at the packing of the cells? How do you design the architecture for them? Because the requirements from the lithium-ion versus the solid-state cells are very different. And so this was one of the early challenges. And then when you look at the materials, obviously since we're working with pack materials, the composite materials, it's very different. And so a lot went into looking at the modeling, the testing, and the validation. And then and then we looked at the manufacturing processes, especially the molding for the composites. And then there's also the issues related to recycling and reuse. Now, we'll talk about this a little later on, but one of the major things is that early on we said, okay, we want to focus on increasing the volumetric cell-to-pack ratio and the gravimetric cell-to-pack ratio. Early on we were kind of conservative about this, but we realized that once we started doing the calculations that actually there is an enormous benefit, especially when using composite housings, that you can gain a tremendous amount in the gravimetric cell-to-pack ratio, and it varies from anywhere from 40 to 82% in terms of weight benefit. And this can be very, very useful in terms of essentially getting a larger amount of range out of a pack of the same mass. At the same time, we also looked at essentially new models for energy storage as a service approaches for stationary storage to help improve or to provide new models for business for the stationary storage sector. And then we are also working with the JRC to explore standards and policy contribution. Training program has been developed, and we'll talk about this later, but as I mentioned earlier, I am the chair of the EU Ingenious Project Cluster, and we'll go over the goals of that later. And so From my side, that's pretty much it. We should move on to, just give me a second. Yeah, let me. Just get that. Okay. And so now, do you want to introduce or do you want me to introduce this? No. Okay. And now I'd like to introduce Katerina Fagiadaki from the University of Patras, who will present the work on the modeling and testing of the composite housings.
Hello, good morning from my side too. Today we will present the work carried out from the University of Patras in the TEMPEST project, focusing on experimental validation, numerical modeling, and sustainability assessment of the developed battery housings. Next slide, please. Here we have all three demonstrators used in the project. An innovative thermoplastic helium SMC with aluminum hydroxide additive is used for demonstrator 1 due to its recyclability and fire retardant potential. And two commercial thermoset A-class SMCs were introduced for demonstrator 2 and 3. Next slide. So in order to achieve the validation of the mechanical response of the housing, the SMC material needs to be characterized. Standardized tests have been conducted, given the mechanical properties of the composite in tension, compression, and three-point bending and shear loading. And here we can see that the material has a transversely isotropic behavior due to its randomly distributed long glass fibers, and shows a bilinear behavior due to its thermoplastic matrix. Next slide, please. So in our work, the validation approach is based on using experimental results to calibrate and validate our models, and then models are used in a predictive way. The goal is not to replace the experiments, but to reduce the number needed. Next slide. So low velocity impact tests were conducted. Okay. Low velocity impact tests were conducted using an Instron drop tower machine, and all tests were performed using a 16 millimeter diameter steel impactor with a mass of 6.8 kilograms, while the impact energy was controlled by adjusting the drop height following the principle of energy conservation. The load versus time response is recorded for its impact event, and impact tests were performed at two energy levels, 7.5 joule and 30 joule for the flat SMC blades, while for the housing, testing was conducted at an impact energy of 30 joules. Following its test, the damage depth was measured at the center of the specimen, where the most significant deformation occurs. The first drop tower model simulates the impact event of the projectile striking the SMC composite, the flat plate, and the setup replicates the configuration of the experimental drop tower apparatus with a steel support base with 4 clamps and a steel impactor. The specimen representing the SMC composite plate was modeled using material model 162 in LS-DYNA, which enables progressive failure analysis of the composite material, incorporating the Hassin failure criteria with the damage mechanics-based softening behavior following damage initiation. The second drop tower simulation model replicates the impact event of a projectile striking the SMC composite housing. Overall, the simulation shows very good agreement with experimental results in terms of damage size, shape, and deformation depth, confirming the model's validity. Its reliability captures damage patterns and force responses across different structural configurations, both plates and housing, demonstrating its applicability for predictive analysis in composite impact scenarios. So here we have two other impact models. The first one being the ground impact, which includes the composite housing, a lid, and a spherical steel impactor representing road debris. The enclosure is modeled using, again, the same material model and is assumed to be adhesively bonded with the lid. The primary objective of the battery housing is to ensure that the protection of the individual cells is ensured. So we model the cell pack as aluminum foil with polymer gel inside in order to model the anode, cathode, and the electrolyte. We also conduct crash analysis using a pole impact scenario. One moment. Another very important sector of the characterization of the dynamic response is vibration. And the main reason we conduct a vibration analysis is to test and identify the resonance frequencies, which may be catastrophic for the vehicle component. To do so, a model analysis has to be executed, resulting in the natural frequencies of each component. Given the natural frequencies and with the implementation of an excitation load over the frequency spectrum, the resonance frequencies are given based on the natural frequencies that display a greater response than the input signal. In our case, 3 excitation loads are selected. Sine vibration profile, which is the most common when it comes to the identification of resonance, a random vibration profile, which is closer to real transport vibration loads, and a mechanical shock, which describes the occurrence of a fast acceleration or deceleration. So regarding the ground impact simulation results, at the lowest impact energy, the housing shows a maximum displacement of 4.7 millimeters, resulting in a 1.3 millimeter residual gap between the cell pack and the first pouch cell, while as the velocity increases, the gap is reduced to 0.65 millimeters. At a higher impact energy, the housing deformation reaches 7.8 millimeters, and the cell pack now comes in contact with the first cell, which shows localized indentation of 2.7 millimeters. At the highest velocity, the first cell is significantly deformed, and the load propagates to the second cell, showing 0.8 millimeter displacement. These results show that at the impact velocities above 20 meters per second, the housing capacity to isolate the cell pack from high energy impacts becomes compromised. This threshold is critical for designing the safety limits of the housing, as direct cell deformation increases the risk of mechanical failure and thermal runaway. Regarding the crash scenarios, the housing absorbs most energy from the impact, resulting in severe deformation without, though, interfering with the cell pack at the first two energy levels. At the highest impact energy, the impact reaches the cell pack, which, however, maintains its structural integrity. For the vibration analysis result, the resonance frequencies are identified for each of the three excitation loads and each of the three directions of loading. The outcome of the vibration analysis is evaluated by identifying the resonance through the peaks of an acceleration frequency curve. Elements from the finite element model of its components have been selected based on the symmetry and the geometry of the components. Its graph includes the curves of a single component, the housing, the lead, and the cell pack, to identify more effectively which resonance derives from each of the three. For instance, in this slide, the response of the sine signal applied in the y direction is presented, and both the housing and the lead resonate at the same frequencies, while the cell pack resonates at two different ones. An overview of the resonance frequencies show that apart from a few ones, the frequencies are the same for every loading. This is encouraging for the suitability of this housing as a battery enclosure, because we see that most resonance frequencies are over 200 Hertz, which is over the range that's typically used in transportation. The fact that all the resonance frequencies are the same is a validation of the frequencies of the simulation that we conducted. However, it can look alarming in the first glance because we applied three different loads and we got the same results. This can be due to the boundary conditions that we used, which were the same for all three loading scenarios, and the fact that the power spectral density curves, which show the signal power over the frequency spectrum, have the same amplitude, which means that the signal is distributed in the similar way for the three loading scenarios. So now we're moving on to the moisture absorption testing, where two types of specimens are used, corresponding to the evaluation of the tensile and flexural mechanical properties. The specimens initially were conditioned for 2 days in an oven to subtract any moisture, and then were immersed to deionized water for 3,000 hours, and their weight was monitored every 7 days to determine the percentage decrease of moisture in its specimen. When the curve of the percentage decrease versus time reached a noticeable plateau, the specimens were considered saturated. The specimens have two thicknesses, which result in different saturation times. And here we can see that for the thinner specimen, the saturation is achieved at 0.75% of moisture absorption, and for the thicker specimen at 0.71. After saturation, 10 specimens were subjected to accelerated desorption by being heated at 50 degrees Celsius for 500 hours to examine how the material will behave after the moisture is subtracted from its specimen. Again, the specimens were weighed every 5 days, and we recorded the decrease in weight. It's very interesting to see that after desorption reached a plateau, the final weight was under the initial one, meaning that some matrix material was diluted. Regarding the mechanical properties, the elastic modulus is more influenced, leading to a decrease of 55% in tensile and flexural testing. And the tensile strength is degraded 35%, while the flexural strength is degraded 39%. The most significant drop happened between the first 1,000 hours when the material absorbs most of the moisture. After desorption, the material showed a slightly higher elastic modulus, but still very much lower strength. Now, two models based on analytical solutions that predict the degradation of the composite's mechanical properties were used to provide predictive capability outside experimental observation. So here we have a linear and exponential model that was used. And we see that the analytical models effectively estimate both strength and modulus, particularly at saturation, which occurs after 2,000 hours. We can see that in the tensile properties, especially up until 1,000 hours, there is some difference between the analytical and experimental results. However, this is due to the fact that tensile properties are fiber-dominated, and while these analytical models are based on matrix-dominated properties. Now we're moving on to modeling and simulation, and once the degradation models were validated at specimen level, they were implemented into previously validated impact simulations. This allows us to evaluate how environmental aging affects structural performance during ground impact scenarios. For instance, here, we can observe that the difference between the dry state response of the housing with the cell pack gets progressively worse from the dry state to the saturation state. Similarly, this is how the battery housing performs under two impact speeds in three different conditioning times from the dry state to saturation. Moving to fire testing, we have conducted a cone calorimetry test where all three SMCs are used. And the helium SMC has fire retardant properties, while the other two materials are used as benchmarks. Cone calorimetry tests were performed according to ISO 5660 to evaluate the reaction of fire behavior, and two thicknesses for the helium specimens were tested, 2.5 and 4.5 millimeters, in order to investigate how the thickness affects fire performance. Also, UL94 tests were conducted to test the flammability of the composite, and full-scale UN ECR 100 tests were also conducted. Now, regarding the cone calorimetry results, the Menzolite and Polytech SMC specimens retained their overall structural integrity despite being extensively burned, but maintained their shape throughout the test, while the helium SMC showed significant structural degradation. The matrix was decomposed, and the remaining structure consisted of primarily the glass fibers. which maintain partial cohesion. This behavior is attributed to the presence of aluminum trihydrate, which undergoes endothermic decomposition. In terms of heat release rate, the cone calorimetry results showed that the helium SMC exhibited significantly lower peak at heat release rate compared to the other two materials. And specifically, it exhibits about 60% lower peak heat release rate. And also exhibits a great behavior in terms of smoke production. It should be noted here that especially the thicker helium specimens shows smoke production after 600 seconds, which is a threshold for fire testing. In the vertical UL94 test, the helium achieved the V0 classification with after flames time of under 1 second for both flame applications, which confirms a self-extinguishing behavior and a high flame retardant efficiency. On the other hand, the other two materials didn't achieve a classification in the vertical test as they burned down completely. This is why the two other materials were tested in the horizontal test, where they achieved an HB classification, indicating that they burned in the horizontal rate at a control rate under 40 millimeters per minute. In the R100 test, the maximum temperatures of the specimens range between 222 and 292 degrees Celsius. The temperatures show a gradual increase during flame exposure, followed by stabilization and a slight decrease after the removal of the heat source. There is a definite, relatively consistent behavior across the three specimen cases and good repeatability of the results. However, here it should be noted that the batteries work at about 85 degrees, so additional thermal management should be considered in order to keep them safe. And here we have the uniform behavior in all tested specimens regarding their after flame condition. They show some deformation due to thermal expansion, but they generally manage to maintain their structural integrity. Now we will move into the socio-economic sustainability assessment that was conducted, which aims to evaluate the environmental, economic, and social performance of the battery systems, including both the battery cells and the composite battery housing. This assessment includes environmental evaluation through life cycle assessment, economic evaluation through life cycle costing, and social impact assessment. The environmental performance based on life cycle assessment focuses on the global warming potential indicator, which is the GWP. It's a metric that quantifies the total greenhouse gas emissions associated with the system expressed in kilograms of CO2 equivalent. It essentially captures the contribution of the product to climate change across its lifetime. At the housing level, the results show that overall demonstrator 1 shows lower CO2 emissions. However, it is interesting to see that the The Polytech thermoset material exhibits lower CO2 emissions per kilogram compared to the helium-based system, but generally have very close results. This is mainly due to the lower energy demand per unit mass and less resin material used. However, when we expand to the full demonstrator, including the battery packs, the trend changes significantly. The battery mass and the material compositions dominate the environmental impact, resulting in demonstrator 3 being the most environmentally damaging. Regarding life cycle costing, we see again that the demonstrator 1 shows the best economic performance, while when we add the demonstrator with the prismatic cells in demonstrator 3, we see how much the cost increases, making demonstrator 3 the most economically burdening. So this slide introduces the social sustainability assessment methodology, where a semi-quantitative scoring system of from 0 to 5 was used, where the higher scores indicate better social performance. The evaluation covers multiple categories, including workers, society and local economy, value chain, and market and social impact. And the results show that all demonstrators fall at the moderate social performance rates between 2.7 and 3.15, with, again, demonstrator 1 having the highest score, which means that it performs better across all social indicators. So in the final step, we combine all metrics in a single sustainability assessment with a score from 0 to 1, with 1 being the best overall score, and using weighing factors for its factor, being 50% for the environmental, 20% for the economic, and 20% for the social. The results confirm that the battery design and system integration play a dominant role, outweighing differences in housing materials, since demonstrator 3 shows the lowest socioeconomic score and demonstrator 1 the best. So we're now moving on to the battery performance testing.
Thank you, Katerina. Yes. Chris Vagg from the University of Bath, and I'm going to present the work that we've led on battery performance testing and also on the verification of the demonstrators. So we started in this task with testing of the lithium-ion cells, which were implemented for the demonstrator number 3. There were also tests on the solid-state cells from ABEE, and those were to go into demonstrators 1 and 2. But to begin with, I'll present the results for the standard lithium-ion cells. So we performed this characterization, and I'll explain a little bit about the various tests that we did. We started with a conventional open circuit voltage test. So this is a pseudo open circuit voltage test at an extremely low C rate, so you can at 0.05 C. You can see the results of that in the bottom left-hand corner. And the perhaps more interesting element to this is we characterized the entropy coefficient, which is a nice piece of data, because it's not very widely, this kind of data is not very widely available. So this is, all of this data will be in the public available results, and it's uploaded to Zenodo. So you can find that in the project results, or if you have any difficulty finding it, you can reach out to us. So this entropy coefficient was really interesting and really useful because we used it as part of the thermal modelling work that we undertook. I'll talk about that a little bit more in the next slides. So beyond that, we did some characterization of the Thevenin equivalent parameters, so the internal resistances and the capacitance terms to parameterize a Thevenin model. And we did that a range of different states of charge and a range of different data, a range of different temperatures. So again, you can see all the results here, and that allowed us to build up a nice representation of the lithium-ion cells in the digital domain, and fed our modelling work. We also did some degradation tests. So we did some capacity degradation checks over 700 cycles, and this was both to examine how the cell performs over the long term. So this demonstrator with the lithium-ion cells, demonstrator number 3, was specifically targeted for stationary storage applications. That was the target application of this kind of technology, and all the technology that was going into it was with that in mind. And so we were doing these cycles with a view to examining how it would perform in that kind of application. So we, as well as just getting the information about how the cell performs, we also sent this aged cell to ABEE, who disassembled it, and the purpose of that was to make the aged or the used, the spent materials from the cell available to NIC, National Institute of Chemistry, who they'll present some results a bit later on about the recycling techniques that they've been working on for recycling battery cell materials. And so following this characterization, we went on to looking at how this can affect the use case in a module or in a demonstrator. So that's what we see on this slide. So we developed an 18S, so 18 cells in series demonstrator for demonstrator 3. And along the way, we also developed a smaller subscale version of that demonstrator with just 4 cells in series to allow us to start the experimental work sooner and start debugging some of the issues we expected to find. So we tested several configurations. We were incorporating technologies from elsewhere in the consortium, including one of the rest-cold coatings for improved heat transfer capability, and we also incorporated some heat pipe cooling techniques. So the individual elements of the technologies you'll actually hear a little bit more about in the subsequent presentation. So the sequencing of the information is slightly out of order, but we'll do a deep dive into the individual technologies in the next presentation. And but what you see here is the kind of final validation of all of the technologies in the demonstrator. So as well as so I mentioned the first configuration with looking at the effect of the rest-cold coating. We looked at the effect of different thermal management strategies, so with a liquid-cooled cold plate and with an air-cooled cold plate. And then we also looked at the effect in simulation of liquid cooling the assemblies. So this was highly instrumented, and I should say if I go back one slide, so what you see on the right-hand side is the demonstrator on the test bed at IAPS, and the bundle of cables is because of the extremely high level of instrumentation that we had, and as well as incorporating a lot of thermocouples. We also incorporated a number of heat flux sensors into the experimental setup, so that we could look at exactly not just how much heat energy is removed from the module, but also by what mechanism it's being removed, and allow us to better understand the heat transfer effects. So this is just an example of the data which we're able to get from the test campaign. I'm not expecting anyone, obviously, to be able to look at any of the detail here, but it's just an example of the sort of data which will be publicly available on Zenodo. The different test numbers, 1A, 1B, 2B, 2C, they correspond to the configurations from the previous slide. At the top we can see the voltages, the cell voltages during the test, and the other graphs are showing the temperature distribution through the module as it goes through the test. So there was one key element that we weren't able to test in experimentally, and that was the liquid-cooled, direct liquid cooling benchmark. So we developed the demonstrator with heat pipe assemblies, but we needed to show, or needed to explore the performance of that thermal management system versus an equivalent with liquid-cooled cold plates in between the cells. So looking at the diagrams on the right-hand side, the one at the top is the one which we had experimentally. So we have heat pipe assemblies in between each of the cells, and they draw heat up to the heat pipe sinks at the top. So we have 4 small aluminium blocks, which are the heat sinks of the heat pipes. And once the heat arrives at those heat sinks, it then needs to be evacuated to outside of the pack assembly. And so that's the job of the top cooling plate. So we have one top cooling plate for the 4 cells, for the group of 4 cells. And that's fed with water. And so we needed then to compare that against a module which directly feeds cold plates in between the cells with water. And we didn't have a version of that in hardware, so all of the data which we collected through the performance testing of the cells is what went into developing the digital twin, which is what we were able to use to explore the relative performance of these different thermal management techniques. So as well as the Thevenin parameters, I just again highlighted, so in bold you see there the dV by dt term, so the entropy term, and we've used that term to really explore how that affects the heat release rate, so the reversible part of the heat release, as the chemical reactions during the charge and discharge release and also absorb heat during the charge-discharge cycles. So I mentioned that we parameterized a digital twin. We took an approach to base this on a lump parameter thermal network type approach. So it's a relatively simplified thermal management simulation, and we wanted to take that approach to see how good a results we can get with a relatively simplistic model. So it's much lighter and much faster to execute than a full finite element type model. But as you can see on the left-hand side, we actually get extremely good results. So this is quite an interesting learning point, that we can get very good results with a quite lightweight model. So in the bottom left-hand side, the lines, you can actually see that you could probably only make out one line, but there's actually a line for the simulation and a line for the experimental data. And you can see the two are almost superimposed, which is a good thing. It shows we've got extremely good results despite the relatively lightweight model. And so the results of that show, well, firstly, in the green box on the right-hand side, you can see at the top, point number 1, you can see the model validation checks. So we're generally getting a mean error of around 1/4 of a degree, so throughout the test. So really good results from the model. And the next most important thing is probably the second point there, looking at the cooling performance comparison. And so this was comparing the heat pipe cooled module versus the water cooled module, directly water cooled module. And we were trying to evaluate whether we could achieve 95% as good a cooling with the heat pipe assembly as we could with direct water cooling. And the results confirmed that, so we had 96% as good cooling with the heat pipe assembly as we did with the direct water cooling. So there was a KPI actually in the project based around this, and we were able to demonstrate that the heat pipe assembly system does achieve that performance. If I just jump back quickly, you'll notice that both the heat pipe assembly at the top and the liquid cooled version at the bottom both have similarly sized plates in between the cells, so they both occupy a similar volume. So the question actually, you know, in terms of applicability and relevance and pertinence of the results, the question really is, why would you accept something which is less highly performing, so only 95 or 96% as good, if it's going to occupy the same volume? The answer, I think, is because the heat pipe assembly will be more robust, so it needs fewer interconnects, and there are fewer points of potential leakage. So we would expect that system to be nearly as highly performing, but more robust to mechanical vibrations and to potential leaks and maintenance issues in the future. The second reason is that it gives you the opportunity to completely remove the need for water cooling. So one of the other tests that we're still trying to process the results of is removing the heat from the cold plate with air cooling. So rather than taking the heat to the top of the module using the heat pipes, but then evacuating that with air cooling rather than with the water-cooled cold plate. So finally, to look at the performance of the solid-state cells, we performed a characterization of the solid-state cells from ABEE, looking at the effect of temperature, and we looked at the discharge capacity and also the internal impedance at a range of different temperatures. And the key thing here was we were interested in the performance at lower temperatures, and in particularly with a view to understanding by how much we might need to heat the cells to get a good performance out of them. Because one of the common concerns with solid-state technology is the need to operate at higher temperatures. And so we found a really interesting results and demonstrated that actually with a relatively small amount of heating, just raising it from 0 to 5 degrees, we already get a huge increase in the available capacity and reduction in the internal resistance. And again, you know, going up to 10 degrees, we get another sizable drop. ABEE conducted some aging tests themselves, and so they demonstrated 85% capacity retention over 800 cycles, operating at half C, and considerably longer, over 1,500 cycles when running at lower C rates. So that's the whistle-stop tour of all of the validation and the verification that we did at the cell level and at the pack level. The testing incorporated all of the technologies from elsewhere in the consortium, so the housing, the battery management system, the structural health monitoring system, and as well as obviously the lithium-ion battery, the system design, also for the solid-state system, and the life cycle and system assessments from Petras. So we'll cover in a little more detail each of these elements and the detailed verification of them in the next presentation. And that's the end of this session. Thank you very much.
Thank you, Chris. Just another reminder for the online participants. The video will be available next week on our YouTube channel, together with the presentations. You can, of course, download them. And for our next speakers, we have Maxim Olive from Resco, and also Stanislav. He will be joining online.
Yeah. Oh, yeah, I see.
Sorry, my bad. So before Maxim and Stanislav, we will present our package tips, the University of Bath.
Yeah, so I'll jump straight in then, yeah. So University of Bath were leading work package 6, so the battery manufacturing. But there are multiple tasks within this. So there's the manufacturing of the battery housing and the disbonding on command assembly. There's the NDT and guided wave structural health monitoring technologies, the battery management system, the various coatings development, and then finally the integration of all of these to the demonstrator production. So I'm going to, we're not going to address each of these in that order because it makes more sense in terms of the narrative to present it in a slightly different order. So we're going to start with the battery housing, and Fraunhofer are going to walk us through a little bit the production of that. And so we'll go through a few different presenters, and it'll come back to me at the end. So Christian, I think you're first.
Yeah.
I'll bring you the. I'll
I
bring
think
you
you can just skip the
Okay,
slides.
okay,
Yeah. Hi. Hello everyone. Christian Stemmler from Fraunhofer Institute. I specialize in design and manufacturing of lightweight polymer solutions, especially in drive systems. So what we wanted to do here, I will focus on demonstrator 3. We talked a lot about demonstrator 1 and 2 earlier. Those have been derived from pre-existing molds. This made sure that we can provide early test specimen for all the verification, fire tests, and so on. However, in remark to the manufacturing, here we came up with an innovative approach, a co-molding process, which is that with this demonstrator 3 we had the highest energy storage, that's thus resulting in the highest battery cell weight, and therefore we needed a really structural, integrative, and stiff solution. And to provide that, here we not only use the SMC, but also a local reinforced fiber profile, which is shown in the picture on the bottom left. So we have the SMC, allium, and also the pultruded profiles, which is basically the same material, just earlier manufactured in a different process with a continuous fiber solution, and therefore giving a local reinforcement. We worked at a mold temperature of 100 degrees Celsius, and especially with allium, we also needed to apply release agent externally, because with this big component with a huge surface, the demolding forces is a challenge. The target weight was approximately 2.8 kilograms, and I will show the manufacturing process now. So we have a mold consisting of two halves, a lower mold and an upper mold. In the lower mold shown on the left, we have grooves that are used to place the profiles mentioned before. So we place them manually, and even though they are maybe not 100% perfect in the geometry because they have a slight spring back, during the process everything is put into position, and this works really well. On the right side, you see the top half of the mold. There you can see all those ejecting pins and everything that makes sure that you can demold it. And also the ribs that are used to position the cells directly in the housing enclosure. For the profiles, we manufactured the allium in a continuous fiber process, so we end up with a linear profile. And that this follows the casing geometry, we had to double bend the ends of sections. And we did this by heating locally in a steel mold that had heating cartridges inside. at 190 degrees. And then we press two parts as shown in the middle. We also have a top part with the same geometry. We push them together and ended up with the profiles shown on the right side. And we could achieve a really high fiber volume of 71%. Yeah, the special thing about this is that compared to other approaches with prepreg, with metallic hybrids, we have only one single material used here, still achieving a higher stiffness. So in perspective to recycling, it's one material, you can recycle it really well. And if this works well, you really achieved something. So here you can see all the profiles set into the mold. In total we used 7 profiles, and after they are placed, we then place the sheet molding compound. And what we noticed is that it's really important how it is placed, or what's the size of the SMC cover, because after placing, everything is pressed together, and then you need to consider the material flow and make sure that the flow does not do any fiber washing or displacement of the profiles. Therefore, you can see the final result of the mats that we used. So we covered all the lateral side and just make sure that only parallel to the profiles the material flow is following and keeping everything in position. And last but not least, on the last picture, you can see the final result of the molding of the housing on the top, and is then ejected afterwards. So as a summary, the process went really well. So we could show that this co-molding is actually possible with a mono material system. With the helium itself, it was quite challenging with the demolding, which is, as you might have noticed earlier in the LCA, we changed to another material, an SMC standard material thermosetting, just to make sure that we have enough test specimen. However, with a look at surface treatment as well as additional additives like curing agents to make sure cross-linking goes faster, that you decrease the bonding. We are still looking into manufacturing it, as this is one of the few thermoplastic approaches, and we are really keen that we can make it with helium as well.
Good morning, everyone. I'm Max Molive, from Rescol. I'm working mainly on debonding on demand technologies, and I will present today this technology and also other smart coatings developed by my colleagues within the TEMPEST project. So first we will start with the debonding on command adhesives, which we call DOCAs within that project. For this specific project, we used a debonding primer, which is triggered. The name within the project is DOCA 150 because it triggers in the range of 130 till 150 degrees C. And this primer was combined with a 2-component flexible epoxy 3M2216 for the bonding of housing components. The final status of all the work we've done within that project for this DOCA system was that we had a limit of the maximum strength of the assembly due to the SMC material, because we easily reached the failure within the substrate, within the composite. But in the end, with this system, we know that for etched metal, for instance, we can easily reach up to 20 MPa, which gives you an idea of the potential of the technology for this DOCA primer plus epoxy adhesive. The final aim, of course, is to do debonding, so to be able to remove the parts, disassemble, and of course manually if we're talking about a workshop with just some operators to do the work for repair or recycle. And we targeted a maximum strength of less than 1 MPa. And it was achieved after thermal triggering. The parts were, for some, even debonded just by the gravity with their own weight. And the temperature was selected to be able to match with the maximum service temperature of the system, which was in the range of 80-85 degrees C, and to keep some safety gap in order to avoid any not anticipated and unwanted debonding. But in the end, the final strength after debonding was very low, and this strength is evaluated by just manual separation after cutting the parts. And the debonding efficiency was above 99% because we have very limited areas still sticking. And then the residues, when you're looking at the part, when they are separated, it's just primer residues that are easily wiped off, so you can easily reuse the parts. On the picture in the bottom, you see just a dummy sample with pull-out, showing you the efficiency in the initial stage, where you can see that easily observe the failure within the composite. And of course, the idea is not to work only on coupons, but that's to go on the demonstrator scale. So we applied the Indar debonding primer, so the DOCA primer, anywhere we needed to bond. So of course, on the edges of the housing where we are doing the bonding for closing the enclosure, it's where you see the blue line, and also at some locations close to the cell stacking. And you will see later on in a further presentation that we were able to do the debonding easily. The work from Rascal was also focused on other coatings with different functions. In task 6.4 and 5, we used the other technologies we've developed to give different functions to the pack, the housing. So my colleagues developed a set of 3 different coatings with cold spray technology. The first one was used for mechanical reinforcement of the composite housing. For instance, if there is an abrasion with a stone or something. A thermal conductive coating, as shown previously by University of Bath, to improve the efficiency of cooling plates, heat sinks, and then a self-extinguishing coating that was used internally in the housing to prevent any fire spread from the cells to the exterior. Quickly, the principle of cold spray is to make a mix between a gas, hot gas, and a powder mix. It can be a ceramic plus polymer plus metal, different possibilities. Then you have a chamber, and you inject on the parts this mix at high velocity, and due to the ductility of the powder mix and also the substrate, you have a nice coating in the end. So it can be automatized. You have no solvent, which is indeed in the end a dry process, which is interesting for industry. And we play with the experimental parameters, nature, granulometry of the powder, process parameters like speed, temperature of the gas. And we were able to do different nice things, like for the mechanical protection coating, we tested the coating on the different demonstrators. First on the coupon, on sample helium plates, it went well. And then on demonstrator 1, so D1 and D2, we got nice results, uniform coatings, but for demonstrator 3, it was more challenging, and in the end, my colleagues were able to have a nice coating only on the reinforcement. Next, the second one was the thermal conductive coating. So it's a mix of PIC and silicon carbide and copper, and at a thickness of 300 microns. Then my colleagues, after nice deposition on coupons, they moved to the real parts, the heat sinks, and it was more challenging. Then they changed a bit the powder mix and parameters, and they were able to have a really nice deposition at a thickness of 100 microns. And they were able to process the 22 heat sinks for next further test by UBAS. Third one was the self-extinguishing coating with flame retardant properties, so a mix between PIC and calcium carbonate. On D1, it was possible to get a nice coating, but on D2 and D3, it was harder. And it's mainly due to the fact that we observed overheating of the demonstrators, mainly due to the mix used for the coating. So for this, it was pretty much more challenging compared to the two other coatings. So it was for the 3 cold spray coatings, functionalizing the housing internally and externally, and we also used, let's say, a more standard paint, which is solvent-borne, but for, again, fire protection, but for that case on the outside of the coating, of the housing. So we used a 2K epoxy intumescent paint that was deposited on the outside of the demonstrators, and you can see that the coating was quite nice and uniform, and we deposited a 600 micron black paint. And the principle of that paint for fire protection is expansion. So when it's submitted to high temperature, you will see the formation of a char, and the char acts as an insulation layer. It's a technology that we are currently using with aerospace partners, for instance. Then the parts, different parts were covered with this black intumescent paint with no challenges. And the last technology we used was a heating paint, enabling to manage the temperature, especially in cold conditions. So we proposed to use the heating paint based on a simple Joule effect. So this is a paint which is formulated to have a specific resistivity. And my colleagues developed different batches of patches. So the patch is a complex system with different layers. The paint is applied by screen printing on the base liner, and then on the opposite side, facing the housing, there is a pressure-sensitive adhesive. So my colleagues prepared different sets based on the design, D1, D2, and D3, and as I said, the manufacturing was done by screen printing. And then you see these patches, heating patches, deposited on different locations of the different demonstrators. Thank you.
Okay, so we go to our first online contributor. So hopefully with seamless technology transfer, Vikintas from KTU is going to explain the progress made with structural health monitoring system.
Hi, Stanislav.
No, it's Vikintas at KTU, or else we can come back to him and continue with the battery management system first, perhaps.
Yeah, maybe that one.
Okay, so we'll skip through the structural health monitoring system, and perhaps if Technica want to talk us through the progress with the battery management system.
Okay. Hello. So we skip to the battery management system. My name is Joseba Izaguirre, head of electronics and communications unit at Technica. We are responsible for the development of the TEMPEST battery management system concept within the project, and just a few words to show you what has been developed. Within TEMPEST project, we faced the challenge of providing an innovative concept of battery management system that should be able to provide not only management of certain configuration of batteries, but also be able to configure several different configurations in different demonstrators, and also integrate advanced functionalities for structural health monitoring, for managing thermal effects, and so on. So finally, it has been developed a battery management system that is based on a modular design approach, composed of a carrier electronic board plus several system of modules that can be plugged in and out to compose different configurations suitable for every demonstrator and for any others. And at the end, this battery management system provides fully integrated functionality including real-time monitoring of the set of batteries, communication interfaces with the different SLEC modules. It also provides internal functional safety mechanisms, and also includes interface with other modules, for example, with the structural health monitoring system that will be explained after, after this part. During the development, of course, we faced several challenges, mainly in manufacturing, but we have been able to address them and also provide some solutions for, let's say, solve any connecting issues for the demonstrators. But in the end, this is, let's say, a first development modular approach in a prototype shape, but this is easily adjusted and configurable to provide final, let's say, versions adapted for every demonstrator. So this can be also tested. Apart from that, the battery management system has also provided innovative approaches, for example, to manage thermal behavior and provide efficient operation by let's say, providing proactive thermal management of the whole set of batteries, so to improve efficient operation. Apart from that, as mentioned before, the whole battery management system provides also internal algorithms to provide reliable and safe operation and provide different conditions, detection of different conditions, starting from more usual conditions such as overcurrent, overvoltage, undervoltage, or zero voltage, to, let's say, more specific fault detections, depending on the combination of inputs and outputs from the different monitoring systems. Okay, just very shortly, a couple of diagrams just to let you see how this battery management system has been designed. This one is more a block diagram with the internal hardware architecture, and there you can see, let's say, the common carrier board that is managing the overall bus bar with different fuses and switches for controlling the whole battery itself. And then you have different modules, a main control unit, a specific unit for the monitoring of the battery pack, and then individual sets of balance board for controlling and monitoring individual set of cells. Additionally, connection with other external modules like the cooling heating systems for thermal management and the structural health monitoring system. And the final image, next, yep, just a more visual approach, just to, you have seen an image previously in the demonstrator 3 explanation, but this is just a more physical approach of how it is manufactured with a main carrier board, and then several additional boards, system and modules that can be plugged and provide different configurations depending on the number of batteries to be managed. Okay, so this configuration has been applied in different versions for the demonstrator 1, 2, and 3. And that's all from my side. Thank you very much.
Great, thank you, Vikantis. So we'll hand over now to ABEE, who will start by presenting how all of these technologies that we've heard about have been integrated into the demonstrators, and they will cover specifically demonstrators 1 and 2, and then I will wrap up with demonstrator 3. So over to Jagadish from ABEE.
Yeah, thank you. Hello, everybody. So, yeah, can you see the presentation?
The green button to go to the next slide.
I can't see the presentation. Should I start? Okay. Hello all. My name is Jagdish and I'm from Avesta. So over here we are presenting the not only as in a cell manufacturing and the providers of the cells. Along that we are the building of the demonstrators for the D1 and the D2. So this task is basically, it's not only, it might be led by Avista, but it's the contribution from the every partners. So here are some the overall objectives for the demonstrator 1 and 2. So the first is like, okay, the Avista is developing the battery for the demonstrator 1 and 2, but we got all the collective information and the components from the other partners, just like the BMS from the Techno and the battery housing and the production unit from the Fraunhofer and the BMS from even the validation and the config files along with the other parts from the Technica and SHM from the KTU. And the heating plates and the additive, the tapes and the extra like we got from the RESCOL. And again, after these, all this assembly, so these gonna the D1 and the D2 demonstrator are going for the process of deassembling and the recycling along to prove this technology, everything. So what we achieved till now in these the work is that like we able to get all the components, assemble all the things together, make the demonstrator 1 and 2, and still there's some tests are going on right now. So we successfully like add up these battery packs now. Okay, basically we have a two different kind of cells over here. For the D1 and D2, we have the port cells, which are the solid state batteries, and for the demonstrator 2, we have the prismatic cells. So compared to this one, the assembling process is entirely different. So even the subunits also rather different. So we integrated this SHM got from the KTU into the same architect for the both D1 and D2, along with the sensors, both the temperature and the voltage sensors. We along the battery housing, we put in a heating pad because basically the cells, when I talk about the SSB cells, so going for the different ambient conditions, like these cells need to be run for certain temperatures to have a better performance. So these temperatures something like in between 35 to 40. So not only we need a heating, we need a cooling plus heating for these systems to work in the proper condition. And along with to have the better heat transfer rates and everything, so these DOC do cover the primers and the additives have been added to the port cells so that they can be dissipate the heat properly, or even they can get in the both directions. And to when we have this battery pack, it has to be fixed within the module. So we have in a very different kind of this additive material which is to be kept. This is the battery pack, which is again attached to this model housing module bottom. Along with, so we have we have this active cooling system over here. It's not only heating, but when the temperature is very high, we have this two AC the fans where they're gonna be automatically work depending on the BMS, how the sensors, so the NTC temperature sensors are measured. So coming back to the first from Avista, so as I said, like we are not only the building up the demonstrator, but we are the provider of the cells too. So these are the prototype cells like developed by the Avista. So initially, before going to any kind of the assembling process, these cells are properly preconditioned, and we checked all kind. The data has been for the characterization of the cell. Like we need a proper data, just like the capacity characterization, OCV, HPPC, and even for these cells, they were set off a test done for the aging performance too. So coming back to the assembly, first when we got the cells, which are the preconditions, so and all the components from the partners, it's not easy to assemble. So we need to make in a proper kind of the steps to follow, where the first cells were kept in the cassette like of a whole cell holder, and after that like we added these corotherm adhesive, which is very fragile. Like okay, when we had to mix in a very equal quantity, and within the 5 minutes this the material gonna be dry up, so we had to make it in a very small quantity, so for the each cell to make it in a very smooth way. And after that, on the top, like we kept in the cooling plate, and over there the Grescol added before there is a primer to it, so that to have a very good contact to these material. So with this one, we have this particular one cassette or the one cell, where we, for the demonstrator one, we added all 15 cells together to make a one battery module, and for the demonstrator two, we have this 32 cells. And coming back to the main point over here, compared to the other prismatic cells, like over here to connecting the bus bars, let's say like the terminals to one cell to other cell, it's not easy. So over here we did the spot welding process to properly weld these terminals from the in a series configuration. So that like also there were some sensors like the voltage sensors and the temperature sensors also kept on the same the terminals properly welded, so that we can read in the proper information. So here is a demonstrator to how it looks. Basically, like they have the two entities, like the bottom and the top. Initially, in the project, like we was thinking only the bottom to use and with a flat plate on the top, but to have to get this gravimetric ratio and the volumetric ratio to be to reach the KPS, let's say that one. So we had to increase the number of cells, so but beginning of that constraint, the size of the battery was increasing. So to deal with that one, now we kept in another the top the housing top, so that we reach the KPIs and even we can test it properly. So over here, this figure shows like all kind of the components which we got from the partners has been assembled properly, and they kept inside the model housing. And now, okay, still we didn't close the housing because of some validation testing. So before sending to the disassembling or the recycling, so this is properly glued together, and then we can ship it. The same things goes for the demonstrator 2. So this is an overall like the view of these demonstrator 2 compared to the demonstrator 1. Over here we have a 32 cells instead of because of the again the space constraints, we divided these 32 cells into the 16 cells each, so that we can put it in the proper way. And again, each like this, all cells are in the series, and they are well connected with the other SHM and other components over here too. So now,
Great, thank you, Jagdish. So I'll take back the mic for the final part of this work package, which is the demonstration or the production of demonstrator 3. So similarly to the other demonstrators, there's a lot of design and integration work involved, but this one's the largest demonstrator physically speaking. So as I mentioned in the previous presentation, we've got 18 large format 280 amp hour LFP cells connected in series. We've got 18 heat pipe assemblies to route in between them. And so that's what you can see on the top right hand side is the assembly with the heat pipe plates in between each of the cells. And then on top of that is the liquid cooled cold plates, which then extract the heat and take it to the outside environment, which you can see in the bottom picture. So in the bottom picture we've got those cold plates placed on top of the heat pipe assemblies. So on top of that, we've got all of the regular connections which we had to design and make. So all of the bus bars and all of the interconnects, and we had to incorporate the structural health monitoring system and the battery management system, which are the two green boards that you can see either side of the demonstrator. So it packaged inside of the enclosure, and apply the desponding on command adhesives. And the other coatings. So all of this was, the final assembly was taking place at the University of Bath's IAPS facility, our Propulsion Systems Institute. And we were coordinating with other partners to get all of the different technologies to our site in the end of 2025 and start of 2026. The build schedule was complicated. I'll show that on the next slide. So it did end up getting a little bit compressed, but I'm pleased to say we got everything assembled on time and got it on the test bed. So as I said, as an example of the kind of the practicalities involved in this kind of build schedule, we had this rather complicated plan for moving parts between the different partners. So one of the case in point, I think, is probably the enclosure. So if you look at the top line, that was manufactured by Fraunhofer and then had to get sent to KTU to have the structural health monitoring system fitted. And then on line 4, so KTU fitted the structural health monitoring system and then had to send it to Rescol for all of the coatings to be applied. And then once they were applied, they sent it to us at Bath for the final assembly. So there's several things like this that had to go between multiple partners in order to get all of the technologies integrated and working together. And so in the bottom you can see on the left-hand side the structural health monitoring system. So this photo was taken as the parts were starting to arrive. So structural health monitoring system in the black box on the left-hand side, and then one of the first heat pipe assemblies that was returned to us from Rescol. So you can see it has a kind of bronze tinge to it. So that's because it's been plated with the Rescol coating for the improved heat transfer performance. And then the bus bars and the cold plates, and then the enclosure, which is with the blue primer applied, and the cells, and you can see the structural health monitoring system already in place inside the enclosure as well, with the ultrasound transducers bonded in place. So we continued building that up. You can see the large picture on the left-hand side is with 2/3 of the cells mounted in place. And one of the things, this is all about learning what are the complications and the considerations that you don't immediately think about when you're integrating these technologies. So one of the things that we realized during the design process is that because of the structural health monitoring system being bonded to the floor of the enclosure, we can't have the cells resting on the floor of the enclosure anymore, because they would interfere with the ultrasound sensors. So we need to have clearance between the cells and the ultrasound sensors, and so you can see that there's a load of spacers that we made placed on the floor to lift up the bottom of the cells a little bit, so that there's a clearance between the transducers and the, as being shown by the mouse there. So we have clearance between the cells and the transducers, so there's no interference. And then on the right-hand side, you can see a couple of images of the final assembly, and all of the instrumentation that's coming out through the trunking in the bottom left. Fantastic. That's the end of the manufacturing. Obviously, we went to the test phase and after the assembly, and that's what we presented in the previous session. So that's the end of this work package. I think we're moving on to Stanislav, who's going to present some of the recycling and reuse strategies.
No, I will present the idea of using the deboning on demand for the recycling strategies and also reuse strategies. Okay, so the idea is to show the work we've done in task 7.1 and 6.1. So 6.1 was for the development of the technology, and 7.1 for the use in demonstrators. But the idea was to take a bit of, to show you the larger picture, because the idea is not to focus only on that project, but what for? What is the use of this kind of technology for the overall EV battery industry? So why debonding on demand is very critical for batteries, for EV and other applications, especially for EV batteries. These components are even more structural, depending on the design, cell to pack, module to pack, and of course pack to chassis. They are submitted to high forces and loads during the service of the car. But of course, joining is one of the favored assembly technique. But then the adhesive must enable crash safety, stiffness, and also other functions like sealing and thermal management, and sometimes all together, which is quite challenging. But in the end, when you're quite happy with the best adhesive you've developed, you have a final issue which is that there is a permanent bonding, so it makes the disassembly very hard and often destructive. You can find on YouTube pack disassembly, for instance, on Tesla cars, and you see, or Polestar cars, and you see how difficult this is to get something which is efficient and fast, and also with no damage to the housing. Then it ends in costly repairs and safety risk and poor recyclability. Additionally, there are regulatory and market drivers. So with the EU battery regulation from like 2023/1542, which introduced a full life cycle and circularity approach, it means that you need to take into consideration design for repair, reuse, remanufacturing, and high quality recycling. And also there is strong pressure for the recovery of critical raw materials, especially in these hard times, and OEMs are moving away from the sealed black box battery packs, so they now want to give other people the possibility to open and repair, swap cells and things like that. So adhesive must be still highly durable, because if you are using adhesive, sometimes it's a frightening technology. But no, it means that if you are forced to use it, it still needs to be very durable, stronger than before, but also no cleanly reversible if you need to do repair or end-of-life disassembly. Here comes the debonding on demand concept. So what is debonding on demand? It's an adhesive system, so sometimes not only an adhesive, but as I will show you, it can be an adhesive plus a primer, for instance. It must provide structural performance in service, and then you need to be able to remove the strength to make it from full strength to almost zero strength under a specific trigger. Of course, this trigger must not be seen in the service life of the car. It can be electrical debonding under low voltage, thermal induction, Joule heating, laser near activation. Of course, with photo trigger, you have the issue of having the photons or the wavelengths through the materials, or design weak links or debonding layers. And the goal is to have something fast, residue-free, non-destructive, and for the batteries, because in the end, the idea is to work in small workshops with low capex and no money, let's say, for costly equipment. You need to find something very smart and cheap. You have some pictures of technologies developed by TESA or Henkel with electrical triggering, which is nice, but has some drawbacks since you need to be very smart in avoiding any weak or kissing parts touching the metals, or to be isolated everywhere in order to be sure that the low voltage you apply is not leading to current flows other than the debondable adhesive, so it can be a challenge. And also you have the picture on the bottom right, which is the stretch release seal from TESA, which is already used in some computers and phones. The idea is to apply a load, mechanical load, which is strange compared to the service life of the product, and to be able to remove completely the seal. For OEMs and battery integrators, there are strong interest for the end-of-life rework. End-of-line rework, if a cell is faulty, to avoid just wasting a whole pack. In-field repair, swapping cells, and also second life battery strategies, and of course the real end-of-life. Our technology, the focus on our technology, this is the debonding on command primer, so add an additional layer, which is heat triggered. But for most applications, sometimes you already use a primer, so it's not a real additional layer. You can see on the top pictures views of other applications, because it's quite a versatile technology you can use in shoes, in phones, in composite materials. We have projects running now with Huntsman, for instance, with skis for debonding. It's easy and non-reversible, meaning that once you trigger in a good heat range, you can cool down the parts and separate them easily. And the substrates needs to be clean, so we have very few primer residues, and they can be wiped off with alcohol. We can reach very high strengths because for some application we can be higher than the 20 MPa range. The focus on TEMPEST, so as I said, we were involved in two tasks, 7.1 and 6.1, sorry, where we adapted the technology to the helium substrate. We reached very high strengths compared to the SMC because we were able to degrade, to have the failure during the loads inside the SMC, so meaning that the adhesive and the primer were not the weak points. And then we went up to the demonstrator level with deposition of the primer on the different demonstrators, and we also used a spare demonstrator part, the D1 parts, to show how we could do the deboning. We didn't do the deboning on final demonstrators because there are logistic issues. It's challenging to move one full package to another place, so we decided to do it on a spare one. In the end, we were able to do the debonding very easily with a simple tool. As I told you, the idea is to use a very simple tool because we use a hard gun. So you cannot use like a robot with a simple, which is a system which is very complex, because in the end, the OEMs want to do it in very cheap conditions. So we decided to test with an hot gun, and we got very nice results, easy debonding and maximum temperature very close to the bond line of 90 degrees C. So it means that at the component level, we would be not more than 80 degrees C, so quite okay with the maximum service life we had in the specifications. To conclude, so the debonding on demand needs to be, it's one part of the technologies and solutions you need to have for the end of life of the battery packs, but it's a strategic enabler because it can be seen as the gate to open the battery pack and maybe to debond other components. So EV battery design are moving towards high integration and structural bonding, so it makes that disassembly a mandatory feature, but critical challenge. Also, you have the regulatory pressure and the circularity needed, so it means that you need to design for performance, but not only, also you need to design for separation and access to the materials. And debonding on demand would allow the OEMs to preserve the structural and safety performance, but also to enable repair, rework, and second life strategy, and improve the end-of-life dismantling and the materials recovery. Overall, the idea is to move from a permanent and strong and functional connection to a controlled debonding control interface to allow the full life cycle and circularity. So it's just not an adhesive innovation, it's part of the whole solution, but in that whole solution, it's a key system to make the next EV batteries performance compliant and really circular. Thank you.
Thank you, Maxime, and thank you everyone for your presentations. We'll have a 15-minute coffee break, and then after that, we'll have a panel discussion with our EU Ingenious cluster. We have Bruno Rodriguez from the Extended Project, and Jeremy will speak about TEMPEST. And people online, I will send you the TEMPEST project video so you can watch it. Meanwhile, we'll have a very needed coffee break. Thank you.
Europe set out to transform how industrial batteries are designed, used, and recycled. The TEMPEST project brought together research and industry to develop advanced battery pack architectures for the industrial sector, driving improvements in performance, safety, and sustainability. Over 3 years, TEMPEST delivered lighter, more compact battery packs, improved thermal management, and safer designs through innovative materials and coatings, achieving up to a 30% performance increase and more efficient cell-to-pack integration. The project also laid the foundation for circular batteries, introducing reversible adhesives for easier disassembly and hydrogen-based recycling processes for graphite and metals. Beyond technology, Tempest leaves a legacy: open-source battery management systems, a skilled workforce, and solutions that support economic growth and Europe's transition to zero-emission transportation.